Hello, the AX344 here. Today, I'm starting off different in my YouTube page. I'm pretty happy with 73 subscribers, yeah, that's for sure. But I'm going to be doing a new computer series. So this will be my AX344 version 5.0. You may see that I've missed out 4.0. I may explain that in one of my computer series. I'm going to be calling them vlogs. Yeah, I know it sounds stupid, but who cares? They're going to be like video logs basically, and yeah, I'm just editing this so I can insert it into my video, basically insert it into front. So this section of clip you're going to be seeing is basically going to be in front of this video. So yeah, well, basically what we're going to be doing in this is just talking about how I'm making the computer. I won't be showing how I'm making this new computer, but I'll be talking how I make it. It's going to be based similar to my previous computers, as you can see. I will continue on with this series, just I may not release it as much as I have before. Also, yeah, the information will always be outdated whenever I release a new video. It's going to be outdated. Some of the informations can be outdated. Like, I know this episode, the protocol's outdated. I've updated it twice now, so, but it doesn't matter because it's still, I'm still going to release it because it still gives you a perspective, because these are all pre-recorded. So as you can see, the date's going to be different to when I'm going to be, yeah, the date in here, I can't actually see that, so 4/6 and it's 8/6, 4 days. So as you can see, there's a different date. So basically, yeah, of course, it's going to be outdated, the information, but it's still going to be fairly relevant to the design and stuff, so I'm still gonna upload it. So yeah, I hope you enjoy these videos, I guess, and well, yeah, when I finish the computer, because it's going to be a very long project, let's hope it's good. Yeah, oh well, yeah, let's, I guess, begin the video. Hello, the Darkness344 here. Today I'm going to be doing a lot of things, basically. I'm going to be showing quite a lot of things off in this video. So, the last video I released, hopefully, was, because I've pre-recorded it, so I haven't released it yet at this time of recording. So I don't know if I'll have that released or a tutorial on the redstone computer released. I don't know. It may be next video, so who knows. But, last video I showed off this computer a tiny bit before it was fully finished. It's a good computer. I've finished it now by adding in the cursed repeaters, and it works. It's actually fairly decent, and I like it quite a lot. Yes, you can see that menacing shadow in the distance. It's a good computer, and it's quite big, you have to admit. I mean, it's small for what it does, but I mean, it's still fairly big, you know, and it's an 8-bit computer, and then you have this 4-bit computer, which is fairly big, right? And they're around the same size, but that's mainly because this one contains a display and more program lines as well as RAM, and this one is a lot less. I keep looking in this direction, but I mean, so this computer's good, it works, but it's missing a few things, and there's a few more things that I want to add to it. Because it's good. I think it has a 23-bit instruction set. It has conditional branching, very simple conditional branching. It's a very, very good starting computer. The same as that 4-bit one over there. That one's just much simpler. So I've been experimenting with serial data. I was going to make a whole video on it, and I still might doing a tutorial or something. I was just experimenting with it because it's a very, very good way of data transmission. So say, here we got a 16-bit encoder and decoder. It basically, I'm going to explain it now because I'm never going to release that video because I've deleted it because I don't think there's too much point. But parallel is your actual individual lines. So say I want to program, in this number in, right? So that's 1, 2, 4, 8. So 8 plus 2, which is 10. So say I want to program 10 in, right? So I have to put 10 down the data lines, and I also have to have another data line just to say send. And it sends it, and it'll update to your number. So say I want to do this instead, add 11, then I have to send it. And I mean, this is one of the fastest, I think it is the fastest data transfer method you can do, actually, parallel data. Just because it's instant, isn't it? Depends on how many repeaters and delay, but it's literally instant. The only problem is that the more data you want to send, this is only 4 bits. Say you want to send 8 bits, you have to double it, don't you? And that's already a lot of lines. So say you wanted to make an IO, right, that only had a few lines. If it's a 4-bit IO, it's not really going to do much, is it? If it's just, that is a 4-bit IO and you're already IO in out, and that's already a lot of lines. So what we use instead is a thing called serial data, and instead of just being a constant thing, it transmits data down just one line, and you have another line for your address bus, of course. So USB stands for Universal Serial Bus, and that USB is serial data, by the way. It transmits with serial. So serial in Minecraft, the maximum speed you can actually do is 10 bits in 1 second. So a bit a tick, right? And so what I have here is a 10 bits per second thing. The decoder is a modified version of my MyZoomer Games decoder, and his encoder is actually over here somewhere. This is his encoder, but I just decided that I would use my own because it uses locked hoppers and observers, and I'd rather not use observers at all, or hoppers for that instance. So I've made my own decoder right over here that's very simple. And I mean, like, I think that English guy 19 once used this decoder. I mean, he's inactive now, but I mean, when he used to upload, I think he used this decoder once. I mean encoder even, I keep saying decoder. But it's basically a tick per byte, I mean bits transferred. And over here I have a 16-bit encoder and a 16-bit decoder. So let's just program in something. So we're going to transmit just some random 16-bit number. So that's just going to be our number transmit. So what we do, program it in, hit transmit or hit send, and it will send it, as you can see, and that is our number. See, the exact same number transmitted through one line, and you can that line can be infinitely long, which is really, really good. So what I have, I've forgotten where I've put it. It's over here. All right. Okay, so it's a very good thing to do. So what I've been working on, you'll see what I've been using serial data for later. I'll explain it to you later. So what I've been working on is a 32-bit instruction set, right? That's fairly compact, and kind of expandable, and it's a fairly decent RISC instruction set. So yeah, it just uses the RISC architecture. So here are the instructions. You have your RAM, your data bus, your ALU, your display, your program counter, and your program counter, but with conditional branching. Those are your basic instruction thingies. So over here, I've got it all labeled out. And so you have your program counter, and you can address up to 16 lines, which is pretty cool. You have your program counter for conditional branching. The 16 lines, the same 16 lines you can address to, just with a different, as the jump command. Then you have the conditional branching, and you have 2 bits, so that's 4 possible combinations that you can use. So 0, 0 could be off, and then you have 3 different types of conditional branching that you can use with this 32-bit instruction set. Then you have your display, you have a clear command, which is useful for multi-operational things, but I mean, it's only here because it's a modified version of RISC. I mean, it should really be CISC, but there's literally no other things that do the same multi-operation per cycle thing, so we're just going to keep it on this, because it's useful. Sorry, that's fly. Update, that basically updates the display to whatever is on your main data line. Then you have your ALU, you have register B, register A, and give output. Give output just puts whatever is in the ALU out onto the main data line, and register A and B inputs to the registers for the ALU. Then you have your ALU operations. It's a 4-bit number, so there are 16 different functions you can use if you program 16 different functions into an ALU. I don't currently have an ALU that can do that, but I'm planning on making one. It's basically going to be this ALU, my 50 subscriber special ALU, just improved a bit because there are some features that it's lacking, like subtraction, and that's really annoying. You definitely want subtraction. So that's the ALU operations, and there is something in the background that's kind of noticeable. Then you have your main mail data bus. No, you have your main data bus, basically an 8-bit data bus. It's an 8-bit computer it can use. I mean, 16-bit computers are good and all, but I mean, if you really want to get advanced, an 8-bit computer is probably easier just because it's smaller. You can make it smaller in general. Whereas if a 16-bit computer, you have to make the data buses much larger. The computer would be larger in general, and which means it would be more inefficient. Then you have your RAM address. So you have 7 bits of addressable RAM, or 8 bits if you use, well, 7 bytes of addressable RAM because it's a 8-bit computer. And you can even have 8 bytes if you use 000 as an address as well. I think that computer uses it. Actually, I'm not too sure if it uses it or not. The tutorial computer may use it. So hang on, let's go see. I think this does use it. So that means bit 0. So hang on, where's the RAM address? So yeah, you have 4 bits of RAM. Well, 4 sections of RAM, which are nibbles. So 4 nibbles of RAM, and because it's a 4-bit computer, and you only have a 2-bit thingy. 2-bit. I've forgotten what it's called. You know what I mean. It's just a 2-bit selector. So yeah, 0 is always on. But that is also because the way I've based my architecture, even though the RAM is says I want to get input, it won't input because you have separate read or write commands, which is over here. So if we go back, you have separate read and write commands, so you can theoretically have 8 bits of addressable RAM. Yeah, and then you have your read and write commands. So I've based this layout, I've put it in a certain way, just so it's the same layout as how I normally build my computers. So you have your instructions down here, you have your program counter this side, your ALU this side, and your RAM that side, and anything else in between. So that's how I normally lay out my computers, and that's how I'm going to lay out this computer, because it's a very, very, very efficient data data flow. It's very efficient in the way it works. And I'm going to base it on a similar architecture to my previous computers. So data comes out of program counter. Data comes out, goes into ALU and goes into RAM, and then data from RAM comes out. Data from ALU comes out and goes into RAM as well as back into main data line. But since this computer doesn't need that, it just doesn't do anything to it. This computer, it will go back straight into the main data bus. But I'm going to cut all this program down, all of this down, by just inputting it right in, because it has 16 instruction lines. And of course, those 16 instruction lines I'm coming to, which they are the best bit, these 16 instruction lines. So as you can see, I've been quite busy coming up with this design. This is a really, really, really cool type of RAM, and it's good. Basically, you have your main data line at the bottom right. So this is the read, and then this is the write section, and you can control read or write with these. So you can either write to it, or you can read to it, read from it. And of course, you should only read one at a time, or it'll get corrupted. It's not dual read. Basically, I've been making a CPU with it. A program storage with it. So instead, normally my program storages just use ROM. So like a line like this, and you put the redstone torch if you want the program to do that, carry out that line of code on that certain line. So instead, however, this is massive, by the way. I've come up with this solution, so it'll basically do the same thing, but instead of a redstone torch, you actually have to specify it in the RAM. So you say, you write to the RAM, whatever, blah blah blah, and I've broken it, but it doesn't matter because it does matter, it's annoying me. There we go. It basically, it's very convenient because it means you can get computers to program other computers, or you can have a separate device to program your computer, and that is where I'm getting to. So what I've been developing is this really cool serial data protocol, right, which is very, very clever, and it allows your computers to talk to each other, send data to each other, and even better, program each other. That is pretty cool. You can get a computer to program a different computer, and in the future I'm going to make the protocol, well, one, it's going to be universal, and two, I'm going to make it so that you can have computers program other computers. That computer can program the original computer with a different program. It sounds confusing, but you know, computerception. Oh yeah. So what we have, I'm probably going to get like copyright struck or something like that. But here we have the serial data that I was talking about. So you have your sending line, which basically is the first bit sent to the decoder just to say, oh, data is going to be coming. And if you didn't have this bit, then it would be a stream of constant zeros and the decoder would not work properly. Then you actually have your data. So you have your data is getting sent. I know it's called something scientific or something, but I've really forgotten what it's called. You have your data being sent, and then you have your data afterwards. So you have 1, 2, 4, and 8. This is your data address. This is what the computer will do with the data. Then you have 1, 2, 4, 8, 16, 32, 64, 128. So 8 bits of data can be sent along this. And this is the just data, and it will just be input. It will only get processed if it says I want to process the data with these lines, of course. Then you have 1, 2, 4, and 8. And these are another 4 bits of data purely for programming another computer, or programming a computer. These data is the line ID, so it says which line we want the program to go on. And I know I could have included it in here, but I mean, I will. So yeah, and it basically, you can send it, this line can be as long as possible, as you want even. It can be sent, and it's received here. So what I've built here is a simple data interception, and yes, I've put repeaters in so it actually works, and I can give you a demonstration. So, problem is with this, is it's only 8 bits of data can be sent at once. And you're like, oh, why not just make it 32 bits? Well, because that will take forever. So we just have 8 bits of data sent at once. And just to make it really cool and compact, you could of course send 32 bits of data, and it would be really fast. It would be like, what, 3.2 seconds or something. But I'd rather just send 8 bits of data at a time. In future versions I can expand though if I really want. It's really optional. Like I can send 1,000 bits of data, and all it would require is one address on my data address. Pretty simple. So the data gets sent, and it goes into here where you have your decoders, and since we're operating on a 32-bit instruction set on my new computer that I'm going to build, it's only 8 bits. How are you going to get 32 bits? What we do is divide 8 by 4, so you have 4 8-bit registers. These 4 8-bit registers act as one whole register for your program, and of course it sends 8 bits at a time. It'll send 8 bits at a time, fill up, and then when it's all full, or when you say it's all full, then you send down a new command down that saying, I want to overwrite what was on a certain line, and you specify the certain line by the last 4 bits. You specify, I want to overwrite this line, and you specify which line you want to overwrite down here, and it'll basically overwrite it. It'll overwrite whatever's on it. And this is really cool because you can, as I've said already, you can get your computer to program other computers, and that is pretty cool. So that is the program memory. So over here is the start of the computer. I had a few issues copying that to there, but I fixed it by just turning my render distance up. If we go over here, we're nearly there. Okay, we're here now. We have a massive program memory, and I've of course divided it into your 32-bit instruction set. Right, that's the 32-bit instruction set, and an extra 4 bits for your I/O. I know I should have included them in the 32-bit instruction set, but for this version I'm not going to, just because I want to make it simple. And of course, this is all programmable, and I'm at the current moment I'm making a program thingy up here where you can put what you want on a certain line, specify the line, which would be like probably over here or something, specify the line you want to program it on, hit program, and it'll rewrite whatever is on that certain line. That's pretty cool, because you can have this device here, you could have it like miles away with the serial data. The serial data transmission would be here, the module, and it's a very good way of programming. So yeah, that's basically what I've been doing so far. So yeah, I hope if you didn't understand this, I'm sorry, but I mean, it's basically what I'm going to do, how I'm going to make this computer. And you could even say this is part 0 of making my new computer, like an update log of how I'm going to make my new computer. So I guess I could make this a series. I probably won't, I might, who knows. If you enjoyed this video, please like and subscribe, and yeah, hopefully I can make this, and I am out. Thanks for watching, see you later.